Hi, my name is Mariem Mezghanni, and I will present our paper, Physical Simulation Layer for Accurate 3D Modeling. Over the past several years, there have been efforts in building generative networks of 3D shapes based on a variety of representations, such as voxels, point clouds, surface meshes, and implicit fields, to name a few. Though remarkable progress has been made in this direction, state-of-the-art approaches focus primarily on geometric or visual plausibility while discarding a key purpose of 3D design, functionality. This leads the generated content to suffer from severe functional artifacts such as physical instability that we set as our target functional constraint in the present work. The only prior deep generative approaches of 3D shapes informed with functional constraints are limited to offline simulation, where the decoded shapes are fed to a traditional physics simulator to evaluate their functional quality. The simulators being non-differentiable, existing approaches leverage the simulation feedback by either updating the training data or by pre-training a surrogate neural network, which results in missing the benefits of end-to-end training. In this work, we combined recent advances in building differentiable physical simulators with 3D generative modeling. To this end, we implement a differentiable point-based physical simulator Psi of rigid bodies using the framework TIFTAISHI. Specifically, Psi computes the trajectory of shape when dropped from a given height under the gravity force. Psi simulates the behavior of a rigid body when subjected to gravity and shape-ground collisions and computes the subsequent shape linear and rotational dynamics for t time steps. By construction, Psi is differentiable with respect to point cloud shape C. Based on Psi, we build a simulation layer that can be plugged on top of 3D shape decoder to assess and promote the physical stability of the produced shapes. In the present work, we focus on SDF-based shape decoder. The first step consists of evaluating the decoded SDF shape over a regular grid G of resolution RG. Then, we extract the point cloud surface by projecting grid centers over the surface using the SDF value along with the normal direction. The extracted point cloud shape is then simulated using our simulator Psi that outputs its dropping trajectory for t time steps recorded by the position pt and the orientation rt of the center of mass at time step t. The physical loss promotes non-horizontal orientations beta and gamma at the final simulation step t. Our physical loss is differentiable with respect to the SDF shape, which allows simulation gradient backpropagation up to the decoder weights. Our model is trained via reconstruction loss that guarantees geometric relevance of the produced shapes, along with the physical stability loss that promotes the physical stability of randomly sampled shapes from the latent space. Our training schema regularizes the decoded shapes and makes new realistic shapes patterns appear in the latent space. As a first application, we consider the task of single shape optimization. We randomly sample latent codes set in from the latent space associated with input and stable shapes. Our goal is to compute the optimal output shape in terms of physical quality while incurring minimum shape variations to preserve the input shape structure. We compare our simulation layer SimL to baseline surrogate model denoted by H. We observe that our simulation layer provides accurate gradient for relevant shape variations, while H gradient is noisy and entails more severe shape changes. Quantitative results also reflect the relevance of our approach in terms of producing better physical quality while ensuring geometric proximity to the input shape. We provide more qualitative results for shape optimization, and we compare the produced shape to trained shapes to ensure their novelty. The obtained results show that our physical regularization proves beneficial to ensure the validity of the generated content and the discovery of novel shapes. We also evaluate how our physical loss preserves the latent space quality for the task of shape reconstruction. Our approach induces a slight improvement over baseline EDIP SDF. Importantly, we overcome the limitation of surrogate model-based approach thanks to our accurate and bias-free physical gradient. Although we focused on SDF-based decoder, note that our simulation layer can also be combined with shape decoders of different representations, such as point cloud, meshes, and spherical primitives. Please refer to our supplementary for more details. To conclude, we introduced a novel end-to-end trainable generative model with online differentiable physical simulation that helps to achieve better performance in terms of physical validity and geometric accuracy. In the future, it would be interesting to extend our approach to other physical properties and other applications, such as single-image 3D reconstruction with limited training data. Thanks for your attention.